Okay, let's get started. This is lecture 4 of the planets. And no, I'm fine, thanks. And today's lecture is going to move us out into the solar system and examine the structure of our solar system, and in particular, how it is we know what we know. And I'll tell you that the theme of today's lecture, while we talk about the motion of the moon around the Earth about the sun, and all the other planets about the sun, the real question is not how the solar system works mechanically like some sort of a machine, but the real question really for all of you is, how did we humans figure out how the solar system works, how one thing moves relative to another? The Earth spins, the Earth and moon orbit each other, they all orbit the sun. How did people figure it out? And frankly, how did they go wrong in their reasoning for hundreds, even thousands of years? And the reason that that approach, that emphasis on how we know what we know is important is that in your own lives, your professional lives, your academic life, even maybe your personal life, you'll run into puzzles and you'll think you have the right answer. And the question is, how many weeks, months, or years will go by before you figure out you actually didn't have the right answer? So we're going to be talking a lot about concepts, theories, and models that work or seem to work and then at other times seem not to work, and how you resolve that discrepancy. So let me start with a few announcements. We're moving into a new chapter, chapter 3. It's a short chapter. You should be able to sit down in a nice quiet place and 2 hours later have read chapter 3 without any trouble. I'll remind you that there are discussion sections going full steam, as well as talc on Thursdays at 7:30, so you can get help on homework both in the discussion sections and in talc. And then, as we will have every week, homework is due Friday at 6 p.m. online. And we'll have a few quiz questions today during lecture, so you might want to get your colored cards out. And I'll make a little announcement about the night sky right now. I hope some of you are beginning to look up when you walk out at night, not just look horizontally and down, but up, because as I mentioned in the first lecture, the brilliant white star Vega is overhead at 8 or 9 p.m. And then off to the west is the orange, yellowy orange star Arcturus. You might be able to see the Big Dipper that we talked about. And it turns out that today is a full moon. So if you're patient and you wait until about 9:30, and if the clouds don't come in, you'll be able to see the full moon rise in the east, as everything does rise in the east. Above the Berkeley hills, 9:30 or 10 p.m., you should be able to see the full moon. Maybe you've been watching the moon the last few nights. It was a quarter moon just 7 nights ago, and then the last few nights it was a gibbous moon, and then tonight a full moon. And of course you can already anticipate that 2, 3, 4 nights from now it will be a waning gibbous moon. I'll review all of that for you. And now today we're going to do something different, which is I'm going to give you an observing project to do for the next month, the upcoming 3 weeks or so. Here is this observing project. All of you should do this. Let me explain what it is, and I'll give you enough details that if you want to jot down some notes, that's fine, but everything you need to know is in the slide, and you all know that the slides are stored in Mastering Astronomy, so you can grab the PDF file of this lecture online, so you don't have to write anything down. Your observing project, if you're up for it, is to detect, if you have good eyes, the motion of the planet Mars in the night sky. Can you see, over the course of weeks, the motion of Mars, the planet Mars, against the background stars? Now, the first thing you're probably thinking to yourself is, well, maybe I can do that, but how do I know where Mars is to begin with? So I will tell you that. Let me first tell you the project, then I'll give you some clues as to how to find Mars in the night sky. The project is this: chart the position of Mars in the night sky relative to the planet Saturn and the star called Antares. I'll show you where they are in a moment. So you're supposed to observe Mars and, of course, Saturn and Antares in the night sky. You should do this at least 3 times over the course of the next 3 weeks. Maybe once per week. If you want to have more fun, observe Mars twice a week or whenever it's clear. So over the course of 3 weeks, once per week or so, observe Mars and make a chart during the next 3 weeks of where Mars is. So I'd like to have all of you draw a sketch each evening around 8 or 9 p.m., it doesn't matter. Or you can take a photo if you're really clever, showing the positions of all 3 of them, Mars, Saturn, and Antares. And then on a piece of paper, 8.5 by 11, sketch, maybe with some buildings or trees or your roommate in the foreground, Mars, Saturn, and Antares. And you'll label each of the 3 dots. Label the dots that represent those 3, and then put it in the corner of the piece of paper, put the date and time of your observation, and then maybe on a separate piece of paper, do it again a week later, and then yet more 1 week after that. So the idea is that after you've made your 3 sketches, you should maybe, if you're observant, see some motion, slight motion of the planet Mars relative to Antares and Saturn. It'll take some careful artistic abilities on your part to locate the dots on your piece of paper that represent where those 3 objects are in the sky, and then write a paragraph or 2. A few sentences is fine with me, 3, 4, 5 sentences, explaining why did Mars move if it moved, and if it didn't move, explain why it didn't move. So just a few sentences or a paragraph or so explaining why you think, given everything you've learned in this course so far, why Mars seemed to move relative to Saturn and Antares. So you have to be a real observant, observational astronomer. Now, how are you going to find Mars? By the way, this is due October 2nd, so you have 3 weeks, a little more than 3 weeks. And again, 1 observation per week would be good. If I were doing it, I wouldn't trust the weather, so I would try to make 2 observations per week in case one of the times the clouds moved in. Now, let me help you find Mars. I don't know how many of you know where Mars is in the night sky right now, but you're about to find out, and Saturn as a bonus. Here's where they are. From anywhere near Berkeley, look toward the south of west. West, remember, is toward the Golden Gate Bridge, toward the bay, toward the Pacific Ocean. Look a little south of west, and you should see, I've done it myself, 3 fairly prominent dots of light in the sky. And they happen to be Saturn, Mars, and Antares. You'll see these 3 dots. Now, if you look carefully, you might see some fainter stars, especially after it gets darker around 8:30 or 9 p.m. You might see some fainter stars around here, these 3 here. That's Alpha Libra, Beta Libra in the constellation Libra. This is Beta Scorpius, Delta Scorpius. So you might not be able to see them, in which case you'll see this in the twilight. If you wait till dark, you'll see the faint stars. If you wait till it gets really dark, you might be able to see the faint stars quite easily. But for my money, it's easiest to just look for the three bright dots. You can see them fairly easily with your naked eye. Okay? So keep this, memorize this. Saturn is on the right, Mars is near here, a little bit toward Antares, and then Antares is over here. This is the way the sky looked a couple nights ago. I'm not telling you what it looks like now because, well, that's part of the project. So that was September 5th. Here we are at whatever we are, the 9th. So maybe Mars has moved a little bit since then. That's up to you to figure out. Here's another picture of what it looked like 2 or 3 nights ago. Saturn, Mars, Antares. Saturn, Mars, Antares. And the question, again, is when you put dots on a piece of paper, noting where they are, the question is, over the course of the next 3 weeks, do you see Mars move? Not an easy observation, I can tell you. You'll want to locate your dots on the piece of paper as well as you can. Don't spend too much time on it, a minute or two, but try to put the relative positions of the dots. You get the idea from the way they're drawn here. Okay? So again, here's the project. It's online, so you don't have to write this down, but the key is to draw a sketch each evening and show the positions of the 3 dots. Label the dots with Saturn, Mars, and Antares, and put a time and date at the bottom of the piece of paper somewhere, so you know when, so you can remember when you made your observation. Okay? So one of the neat aspects of this is you will now know for the rest of the semester where Saturn and Mars are in the night sky. You'll see lots of other stars, but you'll know that 2 of those stars are not stars at all. Okay, so now let me launch into today's lecture. I'll start with an extensive review. Last time we talked about the motion of the sky as we see it, and we talked about phases of the moon. Let me review for you what we learned, and I'll give it to you in a totally different way. You all know that from anywhere on the Earth, you see stars rise in the east, and they set in the west every single night. And the reason is not that they are moving, it's us on the Earth spinning every 24 hours as the Earth does on its axis. And so, for example, from here at Berkeley, if you look east toward the Berkeley Hills, and actually east is that way, I just realized. If you look toward the Berkeley Hills and watch for 15 or 20 minutes, you'll see stars rising up over the hills, getting farther and farther from the hills, moving eventually overhead. And if you look to the west, you'll see all the stars setting in the west over the course of an hour or 2. Here's what the night sky looks like right now from Berkeley, including the stars and the full moon that we have tonight. There's the full moon. You see the stars. Here's the Berkeley Hills. Stars are rising in the east and, of course, setting in the west. Here it is again. This is what the sky looks like at 9 or 10 p.m. as the moon rises. And again, the stars are moving that fast over the course of a few hours because we are spinning toward the east. Here on the Earth, we're getting carried in the spinning Earth toward the east, making it look like the stars are coming up from the east and then setting in the west as we round the corner. What if we lived on the equator instead of in Berkeley? Well, the difference is that if you're on the equator, now you're right on the line that's going due east, and the stars come straight up from the east. So here's what it looks like from Ecuador. Again, you're looking east. Of course, if that's east, north is over here, and southeast is over there. So here's what it looks like from a location in Cameroon in Africa, or Venezuela in South America. And now you might ask, what does the night sky look like if you lived at the North Pole? Well, if you lived at the North Pole, during 24 hours you would stand there looking at the stars, and unbeknownst to you, the Earth is turning every 24 hours. So you would actually be doing this, but you wouldn't know that. You would just see the stars going around in the other direction. You think you're stationary, but you're actually pinwheeling. And so here's what the sky looks like from the North Pole. The stars are just going around in giant circles all the way around you. They never set, they never rise, because you're right at the North Pole, and you always see the northern celestial hemisphere of stars. You can't see the southern stars at all from the North Pole, but you see the northern stars, and they pinwheel around, and actually it's you pinwheeling around. Okay? So you can think about what it would look like at different latitudes, what the sky looks like at latitude 20 degrees or south 40 degrees, and so on. We also talked last time about the motion of the sun during the year. And I explained in some detail that over the course of 1 year, the sun appears to move against the constellations, against the stars. But it's not really the sun moving against the constellations. It's us on the Earth being carried around the sun in the counterclockwise direction. So when you look at the sun, which you shouldn't do, the sun appears in front of the background stars, if you could see them. And I have a little video that shows this, I hope. There you see the sun moving relative to the stars during the course of a year. And it's moving relative to those constellations we talked about last time. The constellations are imaginary groupings of the stars, but they serve as sort of signposts. Here it is again. Whoops. There. So there's the sun moving against the stars from 1 month to the next. And it's not the sun moving, it's us being carried around the sun, so our perspective, our angle with which we view the sun changes as we're carried around, and so the background stars are different because our vantage point, our viewing location, is different as we look at the sun. Okay. And then we talked about phases of the moon, and here they are. There's new, crescent, quarter, gibbous, and full. New, crescent, quarter, gibbous, and full. That's what the moon actually looks like. And we see the phases of the moon, as all of you know, because of the way the sunlight hits the moon and always illuminates one hemisphere of the moon, but it's our viewing angle from the Earth that changes the appearance of the moon. If the hemisphere we see is fully illuminated, if the hemisphere of the moon that we see is fully illuminated, it's a full moon. But as the moon goes around the Earth, we might see only half of it illuminated, a quarter moon, or a sliver, and that's a crescent, because the other half of the moon is being illuminated. So this is a geometry problem with three objects: the sun, the Earth, and our view of the moon, and how the sun light strikes the moon and reflects off of the moon, giving us a chance to see some portion of the hemisphere that's illuminated by the sun. Now here's a question, and you might get your colored pieces of paper out. If you stand on the moon, suppose you took a trip to the moon, does the Earth go through phases? Well, yes, it does. I think you could probably guess that, especially because the word yes is sitting there. But now let's get a little more sophisticated. Suppose the moon is a crescent, and then you travel to the moon while it's a crescent. When we Earthlings see a crescent moon, there it is, what is the phase of the Earth as seen from the moon? Give it a little bit of thought. I'll give you 10 or 20 seconds. What's the phase of the Earth when you're standing on the moon, when the moon is a crescent as seen from the Earth? Let me see your answers. Go ahead and show me your answers. I see B's, colors flipping madly, and D's. Lots of D's, by the way. The D's are winning. And let me just tell you that this problem is a little too hard for me to do. And I'll tell you why it's too hard. Maybe it's easier for some of you if you have good sort of visual skills. Here's why. This is a kind of a problem where it would be best to take out a piece of paper and a pen or pencil and draw the configuration, a sketch, a model of the sun, the earth, and the moon with an angle between them that gives you the crescent moon that you see from the earth. In other words, it's better to take out a piece of paper, draw the sketch of where the sun, earth, and moon must be to give you a crescent, and then ask, well, what if I stood on the moon and looked at the earth, what would I see? How much of the earth, what fraction of the side of the earth that I see, what fraction of it would be illuminated? That's the only way I can do this problem. And I'm making an important point here. When you have any kind of a challenge in life that involves something moving, some configuration, maybe some geometrical angles, something maybe changing with time, it's a great idea to stop, get out a piece of paper, draw a sketch, and try to understand if the sketch gives you a boost, a crutch, a model for you to kind of lean on, and then come up with a sophisticated answer using that sketch as your model. I mean, if you're, a member of the soccer team or the football team or a basketball team, you all know this is what you do. You sketch the play, where the offensive players will be, the defensive players. And it's certainly true in physics and chemistry and environmental science and biology. You sketch and use that model as a helper, a crutch to lean on. And in this case, if you did make such a sketch, you'd indeed get gibbous moon as the phase of the Earth. I almost said it wrong, the phase of the Earth as seen from the moon. Now, if you were on the moon, here's what the Earth would look like during the course of a month. There's the Earth. By the way, a nice gibbous Earth. Let's see if I can get this to play. There's what the Earth looks like. It's spinning on its axis. You're watching it from the moon, but you're going around the Earth because you're on the moon. So you're orbiting the Earth from your vantage point on the moon. There's a crescent Earth. There's a new Earth. Where's the sun? Oh, there it was. It has to be back there because it's a new Earth. And now there's a crescent Earth. The sun must be over here somewhere, right? Back illuminating the Earth. There's a nice waxing crescent Earth, quarter Earth, waxing quarter or first quarter Earth. I'm going to show that again because I love this thing. So here's a gibbous Earth. The sun must be over here illuminating that quarter Earth from the upper left. Now the sun must be behind. It's because we're orbiting the Earth, of course. And now the sun must be behind the Earth. And as we, on the moon, orbit the Earth, the angle between us, the Earth, and the sun changes. So we see the Earth go through phases. And of course, the astronauts saw that all the time. Now, there were some homework problems on eclipses, and you might have read the chapter or figured it out. Let's talk about eclipses for a few minutes. This is new. We didn't discuss them last lecture. We're going to talk about the two types of eclipses: solar eclipses, eclipses of the sun, and lunar eclipses. Let's talk about solar eclipses first. A solar eclipse occurs, the sun gets blocked out when the moon gets in the way. If the moon is in the way, you can't see the sun. If the moon lines up with the sun, the moon being much closer blocks the sun. So that's a solar eclipse, and you can see the sketch down here. The sun is over to the left. Watch this carefully. Sun is at the left. What's this? Oh, that's the moon. You see the hemisphere illuminated. Sun hits the moon, blocks the light from hitting a very specific location on the Earth, right there. That spot, if you happen to be standing there in wherever that is, northern Peru or Colombia or something, you would not see the sun because the moon's in the way. By the way, if you're not there, if you're over here in North America, well, you can look over here at the sun easily. So solar eclipses are very local. There's only a little spot where the umbra, the darkest spot, totally blocks the sun out. So here's the summary. The moon is in front of the sun during a solar eclipse. If that's true, then of course it's a new moon, right? You can't see the moon at all because the sun is behind it, illuminating the backside of the moon. And if you're in a solar eclipse, you are in the shadow of the moon. Cool. And the darkest spot of that shadow is called the umbra. That's that spot right there. Now, the umbra moves every minute, minute after minute. Why? Well, for a couple of reasons. The moon is orbiting the Earth, so the shadow will move, but also the Earth is spinning on its axis. So the dark spot moves on the Earth because the Earth is turning, spinning under that dark spot. And now we're going to try to do something really fun. If this works, I'll be so happy. Well, I have some hope. Here we go. This is going to show you an animation of how the eclipse works. Maybe. Hang on to your hats. Okay, so now you can see again the same picture. Moon, Earth. Where's the sun? Oh yeah, it's over here to the left. Sun's rays illuminating the moon, blocking the light that would have hit the Earth. And now the hard part. Yeah, I don't know if I can do this. We will see. I don't think so. Yeah, I'm not able to do this. This is a heartbreaker. I lay in bed at night over the weekend wondering if I'd be able to get these to work. I don't think I can. If anyone has a suggestion, let me know. Sorry? Space bar? Oh, okay. Nope. It's a good idea, though. Sorry?
Hit the play button on the website.
Hit the play button on the website. You mean right there? I can't get the cursor there. That's the problem. My cursor, wait a minute, maybe there's a way. Ah! Oh, I'm so excited. This is the best day of my life. It came in from that away. Now I see. Okay, you ready? Woo! There it goes, the eclipse. That's pretty good. So you see what's happening. This is an incredible discovery, astronomical discovery. So you see what happened as the moon orbited the Earth, the shadow of the moon moved across the face of the Earth, and if you were right at that red dot, you would have seen a total eclipse of the sun. And in the upper panel, you can see what the sun would look like if you lived there. So let's try to do this again. You ready? Here we go. So that's what it would look like if you lived at that red dot there in the southern hemisphere. And now that I'm here, I can do the great trick. Oh, incredible. High technology. Yeah. Okay. So that was good. That's a solar eclipse. Let me show you some pictures of what a solar eclipse looks like. Yes?
How far north or south do you have to be to never experience the solar eclipse?
Oh, solar eclipses occur all over the Earth eventually.
Even on like the North Pole?
Even on the North Pole. Yeah, you'll see it in a second. So what do solar eclipses look like? Well, you can travel to one. There's usually about one per year, but you have to get in a plane and travel there. They look like this. The sun is blocked out. You can see the dark moon. That's a new moon in the way, and it looks very dark. The birds start tweetering as if it were twilight or nighttime. All of the nighttime animals come out. They think it's nighttime, so it's quite funny. Here's a picture of a solar eclipse seen from the Russian space station Soyuz. Oh, Mir, sorry, not Soyuz, Mir. So there's the dark shadow of the moon. That's the shadow of the moon on the Earth. Isn't that cool? Now, here's more about how they work. You might ask, well, gee, if it's just the alignment of the moon blocking the sun and the moon goes around every month, we should have a solar eclipse every month. Every time the moon lines up with the sun, we should have a solar eclipse. But we don't. And the reason is that the moon's orbital plane is tilted 5 degrees to the orbital plane of the Earth. And you'll see that here. You're seeing the Earth, the moon in its tilted orbital plane, and here's the sun way over here on the right. And now let me show you what happens as the moon orbits the Earth. Watch for the tilted orbital plane. I hope. Here we go. There's the moon orbiting the Earth. But it's not in the same plane as the Earth's orbit around the sun. Tipped 5 degrees. And so the moon doesn't get in the Earth's shadow, nor does the moon itself get in the way of the sun very often because of that tipped or tilted plane. Okay? So it's rare to have a solar eclipse and a lunar eclipse, as we'll discuss in a minute, because of that slightly out of that tilted plane effect. Cool. Here's what a solar eclipse looks like, sped up about a factor of 10. The sun is blocked out by the moon, the new moon. Take longer exposures when you get to totality. At totality, the gases around the sun called the corona light up. Take longer exposures to see that faint coronal gas around the sun, and then the eclipse finishes. Here's another one. Oh, hang on a second. I have sound for this. These are actually some astronomer friends of mine who were doing some research, and you can hear what they're saying during their filming, videoing of the eclipse. This is an eclipse in India about 20 years ago or so. People get so emotional. I don't know why they do that. About 2 years ago, we had an eclipse here on campus, it turns out. And here's a picture. I went out to Sproul Plaza with eclipse glasses that I gave out to thousands of people. And you can see the people there at Sproul Plaza with their eclipse glasses on, looking up at the eclipse. Well, that was a lot of fun. And here's that same day, that was May of 2012. Here's, there are some solar eclipses coming up, total solar eclipses. I'm going to tell you about a partial eclipse soon. Here are all the predicted solar eclipses coming up. Total solar eclipse predictions. And notice this one right there is the really great one coming up. 2017, which I guess is about 3 years away. A total solar eclipse goes right through the United States. You have to be on that path of totality to see it. So you should make your hotel reservations now, anywhere along. And I'm not kidding, I already have mine I'm going to be in the Grand Tetons just south of Yellowstone National Park right there. Already have my reservation. And even though it sounds crazy, believe it or not, all of the hotels along the path of totality get booked up like a year or two in advance because people are seeing this. So, you might want to book your hotel room now, or book your hotel room for an hour's drive away and then rent a car and drive to the path of totality. We have arranged for a partial eclipse of the sun during this semester, and it's actually coming up in about 5 or 6 weeks. We're going to have a partial eclipse, and it's going to be October 23rd, as you see here, just before class. So if you come a couple of hours early for class between 2 and 4 p.m., here's the path. It's a partial eclipse, so it's sort of a broad path, and you see that Berkeley gets a nice view of it right in here. So between 1:53 when it starts and 4:30 p.m., put this on your calendar, I'm not kidding. Before class, you'll be able to see it. It lasts for about an hour and a half or 2 hours, as you can see. So you'll want to tell your friends about it. I have already purchased eclipse glasses for our class. So I'll tell you when we get closer where I'll be so you can get the eclipse glasses from me. I'll be probably out on the mining circle, grassy area right outside Pimentel. So we're going to have a partial solar eclipse in 5 or 6 weeks. And even more exciting is the prospect of lunar eclipses of the moon. In some ways, they're more rare. And in that case, how does a lunar eclipse happen? Well, the Earth gets in the way of the moon being illuminated. So the moon, which would be a full moon, here's the sun, Earth, and moon, the moon's light gets blocked by the Earth. And so as the Earth sits here, but the moon orbits by in its path around the Earth, the moon gets in the shadow of the Earth, and so the sunlight that would have hit the moon gets blocked by the Earth, and the moon winks out. Well, not completely. Why doesn't the moon completely wink out? Because sunlight can pass through the Earth's atmosphere and bend by refraction. And so a little of the light gets bent by the Earth's atmosphere and makes the moon look kind of mysterious. Here's what it looks like. That's the moon during a full lunar eclipse. And here again is the geometry, sun, Earth, and then moon trapped in the shadow of the Earth. And you can see there's a darkest part of the shadow called the umbra, and then up here is called the penumbra, where it's not quite as dark. Yeah.
Didn't we have one of those like 4 months ago?
They happen occasionally. You have to be in a certain place on the Earth to see them. And luckily, we have one coming up here that we've arranged for this class. Again, Berkeley is an amazing university. Here's the one right there, and you might be thinking of the April one that you see just above it. But there we are, October 8th, 1 month from yesterday. Isn't that cool? So we're going to have a lunar eclipse. That's the good news. Also good news, it's a total lunar eclipse. As you see, a total lunar eclipse. There it is. Now the bad news, you have to get up at 3:30 in the morning. So, because of course, if you think about it, a lunar eclipse only happens when it's a full moon, right? Sun, Earth, moon, you see the hemisphere fully illuminated, and then the Earth gets in the way to block it. So a full moon is only going to happen at nighttime, obviously, because we're seeing the moon. We're not on the sunlit side of the Earth. And so you have to get up at 3:30 or 4 a.m. to see it. And I'll tell you more about it when we approach that date, which again is only 4 weeks from now. I think it's a Wednesday morning, if I recall correctly, at 3:30 or 4 a.m. You just got to set your alarm, wake up all of your housemates. They'll be so happy that they lost sleep because you showed them a lunar eclipse. Now I'm going to change topics a little bit. We're talking, obviously, about the clockwork of the solar system, how the phases of the moon work by that geometry, how eclipses happen and that geometry. But what about the solar system as a whole? How do we build a model, a geometrical, conceptual framework of the whole solar system? Well, let's start with the moon. One of the aspects of the moon that needs explanation is why it is we always see the same hemisphere of the moon. You in your life have never seen the backside of the moon. You never get to see the backside. You see the front side of the moon. All of you have seen that with your naked eye. But why don't we get to ever see the backside of the moon? And the reason for it is described here. You could imagine the Earth being here, and this person represents the moon. If the moon went around as shown here, well then from the Earth, we would get to see the moon's one face, the side, and then we'd see the backside of the moon, right there, and we'd see the side and then the front side of the moon. So the way the person here is going around the Earth is not correct. It's not correct because the prediction is we should get to see the backside of the moon as well as the front side of the moon. So there's another model, another theory, a concept that explains why it is we only see one side of the moon. And that concept is shown here. Here's the Earth. As the moon goes around us, the moon must itself pinwheel around, i.e. rotate or spin, in sync with the orbit so that the moon spins 90 degrees when it goes 90 degrees, and then the moon spins 90 degrees when it goes 90 degrees, and so on, so that from the Earth we see face, 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 face. The point here, and this is a simple one, but it's a very succinct one, is you can draw on a piece of paper a sketch of a model or a theory, and then ask, does the theory agree with your observations? And in this case, we have a simple observation. We only see one side of the moon. How do you explain that? It must be that the moon spins at the same rate that it orbits the Earth. Yeah. Yes. But I'll tell you his question again. He said, is that what you call tidal lock? And it does have to do with tides, and we're going to talk about that in a couple of weeks. Yeah. Now, that's one model that's a nice one, and here's the bottom line. The bottom line I don't care about. What I do care about is that you can build a model of anything in life, whether it's biology, chemistry, the environmental issues, physics, astronomy. Build a model, and then let the model make predictions, and then compare the predictions to your observations and ask, do they agree? If they do, great. If not, throw out your model. So that's the basic idea. A conceptual model must explain all of the information, in this case, motion of the moon or the planets or whatever it happens to be. In astronomy, you have data that involves the positions of, the visibility of, the phases of the objects, and your model better agree. If it doesn't, throw out your model, it's wrong. That's the nature of science. So now let's talk about the motion of planets relative to the stars. This is related to your observing project. You actually have a lot of data that you can take with your naked eye of the solar system, data that must be matched by a model. For example, the planet Mercury. Probably very few of you have ever seen the planet Mercury, but I can tell you, you can look at it, and the planet Mercury is always close to the sun angularly, 5 or 10 degrees away from the sun. Why is the planet Mercury, wherever the sun is, the planet Mercury is not too far in angle away from the sun? Has to be a model that explains that. Venus, it's always bright. It's also angularly close to the sun, so much so that you only see the planet Venus just after the sun has set in the evening, or just before the sun rises in the morning, Venus being angularly close to the sun. Why? What can explain that? Mars. Mars is the most interesting planet in terms of its motion, because not only is it noticeably orange, which, by the way, you will see when you find it in the next few nights, it's yellowy orange, but moreover, Mars moves against the stars, and here's a clue to your observing project. Mars always moves relative to the stars from the west toward the east against the stars, except when it doesn't. Every once in a while, for a month or two, Mars turns around and goes backwards, not west to east, but east to west for a couple of months, and then it goes back on its merry way, moving west to east against the stars. Why, oh why, does Mars change direction? There has to be a good reason. And even the Greeks, 2,000 years ago, knew that Mars occasionally went the wrong way. Jupiter, same thing. It's bright, moves west to east. There has to be an explanation for why Jupiter goes west to east against the stars. Saturn, same thing. It's less bright. Why is Saturn less bright? There has to be a reason, but it moves slowly from west to east. Why are the planets moving the way they do? Well, clearly, if you lived a couple thousand years ago, or even 1,000 years ago, you'd look up into the night sky, you'd see all this motion. Obviously, you're stationary. Just look at us in this room. We're all stationary relative to each other. Come back in an hour, we're still stationary. So the Earth is obviously stationary, and everything else is moving around us. And so you can construct a model of the solar system in which we on the Earth are stationary. How could it be anything else? And here is that model. See if I can do it. There we go. Earth is stationary at the center. There's the sun going around us. The planets are going around the Earth. One of the planets, Mercury and also Venus, are orbiting the sun. But this is clearly what's going on in the universe, because we're stationary, so those guys are the ones moving. And by the way, here are all the planets. Well, the sun isn't a planet. There's Mercury, Venus, Mars. Every once in a while, Mars goes backwards. You see the little curly-Q loop-de-loops that Mars does? That's that backward motion. Perfectly reasonable model of the solar system. We are obviously not moving, they are. You simply have to explain why it is occasionally a given planet, occasionally like Mars does, goes around and then it goes backwards for a few days or weeks. Has to be a reason for it. So the Greeks thought deeply about the model of the solar system, and they noted planets move from west to east against the background stars, but occasionally Mars and even the other planets go backwards. Why does that happen? Well, the Greeks came up with a theory, and the theory was simple. You simply have a solar system in which the planets occasionally back up in their motion. Seems logical. They were smart. They came up with the best mathematical model that they could. By the way, here's a close-up of Mars going backwards. There's Mars going from west to east, perfectly normal, except occasionally. This is exactly how Mars moves over the course of months. Night after night after night, you watch and Mars goes backward a little bit and then goes back on its merry way from west to east. Why does Mars undergo retrograde, as it's called, retrograde motion? Well, here's what the Greeks figured out. There's the Earth, stationary. Here's Mars going around the Earth. Every once in a while, Mars backs up. Why? Because Mars is not only on one orbit around the Earth, it's on a second orbit, a so-called epicycle. Mars is going around in a little orbit superimposed on the big orbit, so that as Mars goes this way, but it's also going around this way, occasionally Mars is on its little epicycle orbit and is going backwards, and then it goes forwards again. One little orbit superimposed on a bigger orbit allows Mars occasionally to go backwards. So it's a very logical model. The Earth is clearly at the center. The Sun orbits the Earth. The planets orbit on small circles in addition to the big orbital circles. And the small circles were called by the Greeks epicycles. This is a simple model that preserves the obvious intuitive fact that the Earth is stationary. There is, however, another explanation. It's an explanation that puts the sun at the center. Let's see what that involves. Here it is. There's the sun. Here's the Earth going counterclockwise in its orbit. And here's Mars also going around the sun in its orbit. Being farther from the sun, Mars goes a little slower. And so as the Earth goes around the sun and Mars goes around the sun, the Earth passes Mars on the inside track. Have you ever been in a car on the highway and you look at the car next to you, and that car next to you suddenly appears to be going backwards? And it's because from your frame in your car, that car is going a little slower, and it appears to be going in retrograde, if you will, backward motion. That's what happens. The Earth is going faster than Mars, and so Earth is passing Mars around the bend on the racetrack. And so it just appears that Mars goes backwards. The planets normally seem to be going eastward, but as we pass them by, Mars simply appears to be going the other way. So it's a perspective effect. Now, it was pretty brilliant for people to think of this, and even some Greeks thought of it, but the theory didn't take hold because people said, yeah, but come on, we're not going around the sun, we're stationary. So the model didn't catch on for hundreds and hundreds of years. But let's compare the two models. Here they are again, the geocentric model and the heliocentric model. Here's the geocentric model, the Earth And all the planets going around, they're on their epicycles, and it's those epicycles that cause the planets to go in retrograde motion occasionally. It looks sort of laughable after a while, like, come on, can the universe be this way? So here now is the alternate model where the sun is at the center. And the planets are simply going around the sun in nice, neat, nearly circular, but not exactly circular, orbits. And we pass up, there's the Earth, this little circle with the cross. We simply pass up Mars on the inside track. And when you look at this model, you can just feel it in your bones. There's a simplicity. We aren't concocting circles upon circles, maybe upon other circles that are made up. Ad hoc would be the word. But instead, there's just one center, the sun, and everything is going around the sun in simple motion without any concoctions. So there's an elegance, you might say a beauty, a simplicity to the model in which the sun is at the center rather than the Earth. Of course, there are many, many other reasons to realize that the sun is at the center, and I'll talk about it in a moment. But let me first point out that for thousands of years, this was a debate. And you can easily see that the geocentric model has appeal because we are so obviously stationary. And yet, the heliocentric model wins out because of its sheer simplicity. And so as a general rule of thumb, the best model or theory or concept is the one that makes the fewest out-of-the-box guesses or assumptions or conditions. And the geocentric model has to have those epicycles. And there's a rule here called Occam's razor. Occam's razor is a rule of philosophy that says if you're confronted with 2, 3, 4, 5 different options, theories, models, the simplest one should get your preference. It's not necessarily right, but it's probably right, and it has appeal because of its simplicity. So Occam's razor says, choose the simplest model that explains all the data. If you take more data and the data disagree with your simple model, you have to throw your simple model out and go on to the next most complicated model. So here's the 3D view of the solar system. You have the sun at the center. The planets all go around the sun, all 8 major planets, and even the dwarf planets, Pluto. And they all orbit the sun in a flattened plane, nearly circular orbits, not perfectly coplanar. And that's a very simple model of the solar system. But is it right? Is there a test? How do we know that this model with the sun at the center is right? Well, there's a great test. It's incredibly definitive, and it's called parallax. The Greeks understood that there was a test, and the test was simple. And let me tell you again why the Greeks hung on to the geocentric model and rejected the heliocentric model. The Earth can't orbit the sun because it runs counter to your intuition. Every day the moon and the stars and the planets seem to go around us, not the other way around. Moreover, if the Earth were actually spinning on its axis, wouldn't we feel a wind? If you're spinning and there's all this air, why isn't there a wind rushing by as we spin under the Earth's atmosphere? And here's the kicker. This is really important. If the Earth goes around the sun, then as the Earth goes around the sun, we would view the stars from a different perspective every 6 months. You start over here, you orbit around the sun, you view the stars from 2 different angles. That should make the stars appear to move just because of our different vantage points. So, did the Greeks observe parallax. Here's the sun, there's the Earth in January. You wait 6 months, observe a star. In January, the star appears that away against those stars. 6 months later, the star appears this away against those stars. We should see stars move every 6 months. And if you've never dealt with parallax before, let me ask you to hold up one finger and close one eye and line it up with me or anything else. Close one eye and look at your finger, and then close the other eye, like that. You don't have to make that sound, only I can make that sound. But when you view something from two different perspectives, it appears to move. You're viewing it from a different angle. The Greeks tested this. They measured the positions of the stars very carefully, and they looked to see, during 6 months, did the stars appear to move, and they did not. And so the Greeks, with their great knowledge of geometry, said, aha, we've ruled out the heliocentric model. The Earth must be the center of the solar system, because we don't detect parallax. Very logical. Good test. Moreover, you would have to rule out the heliocentric model because you don't see parallax. So your data disagree with your prediction from the heliocentric model. Fair enough. The stars' positions should have changed. The Greeks did not detect parallax. They tried, and therefore they ruled out the heliocentric model. But there's one fly in the ointment. There's one way that the Greeks messed up. They couldn't be blamed for it. It turns out the reason they didn't see parallax is that the stars are simply too far away. When stars are very, very far away, light years of distance, as we get carried around the sun, the two vantage points separated by 6 months is not enough to see the position of a star change due to our different vantage points. The Greeks didn't realize how unbelievably far away the nearest stars are. Remember our model solar system with the grapefruit? And the nearest grapefruit was in New York City. So the Greeks shouldn't be faulted. They debated, they took data, but it didn't work out because of the great distances to the stars. So now the heliocentric model works. Oh, I forgot to mention. With modern day telescopes, we can point at stars and easily see parallax. Easy. You just point at a star, come back in 6 months, look through the telescope again, and the star moves quite dramatically. Some stars, move a whole arc second. They move relative to nearby stars in the telescope. So without a telescope, the Greeks had no chance. Does parallax depend on your location on the Earth? Not very much, because here's the sun. We get carried around the sun. Where you happen to be on that little blue dot called the Earth hardly matters, because the little blue bead is so small compared to the size of the orbit of the Earth that where you are on the Earth doesn't affect the parallax. There is a little bit of parallax, but not much. So this yields a broader discussion of what makes a good theory. And let me summarize. It's natural to imagine various theories. Human curiosity leads to the desire for explanations. How does the universe work? How does nature work? But we sometimes get the wrong answer. So you try to come up with concepts, understandings, truths that should be in quotation marks that explain the data. And then you draw conclusions about the best model, the best theory. Maybe your theory is wrong, you throw it out. That's a trial, but it's wrong, so it's an error. Try again with a new theory, throw that one out. And eventually you might come up with a hypothesis, a theory. And by the way, the word hypothesis and theory, they're very similar words, so I don't distinguish between the two of them. You make a hypothesis, and then you do an experiment, or take data, or do some observations, and ask, is your theory supported by the data? You can't prove a theory. You can only take data, make observations, and say, oh, the data agree with the prediction, i.e. the data support the theory, but you never prove anything. That's why you hear about the theory of evolution, heavily supported by hundreds of thousands of biology experiments. Evolution is right. But you never really say it's a fact, because the scientific way is to call it a theory forever. And here's one of the tests that you can do when you're in the grocery store. You might be thinking to yourself, gee, I'd like to lose a little weight. I better think about what food to eat. And a pretty controversial issue is whether eating pasta, spaghetti, and so on makes you fat. Carbohydrates in general, when you eat carbohydrates, bread, pastas, does it make you fat? Well, one way to test this is go to the supermarket for a month and buy lots of pasta and eat lots of it and put yourself on the scale, and then take data on the scale and see how it goes. Then go another month and don't eat pasta. That's a perfectly good scientific method. Science isn't really special. It's just logic. It's just rational thinking. Science basically says, come up with an idea, call it a theory, a hypothesis, or a concept, whatever you want, and then take some kind of data to test whether you're right or not. Most of the time you're wrong. I mean, let's face it. In life, you come up with an idea, and a lot of times it just turns out to not be right. If you're honest, you realize, and that's because the world is complicated. Science recognizes that and is humble. Scientists are humble in the sense that if you have an idea, test it with data, the data do not support the model, you throw out your model. It's wrong. You were wrong. Just the way it goes. Some of the historical scientists who realized all this, I'll mention a few of their names. Nicholas Copernicus from Poland. You can go and visit sites where he lived, as I have done. Copernicus was the first person to say, you know, these epicycles really are concocted. They're ad hoc. They're made up, contrived to just explain Mars's retrograde motion. It's artificial. A better way is to let the planets orbit the sun. And he wrote this book, and people told him he couldn't publicize it because it was heretical. Yeah.
Wasn't Aristarchus the first?
As I mentioned, you're right, there were Greek philosophers who indeed anticipated the sun-centered model, for sure, but it didn't catch on. Copernicus had a sun-centered model. Sun is at the center. Earth orbits like any other planet. The inferior planets, the ones close to the sun, hug the sun, and that's why they're angularly close, like Venus and Mercury. And then retrograde motion occurs when we lap a planet. So the heliocentric model invented by Copernicus, maybe not invented is not fair, but he certainly argued the case for its value so strongly that it took root. And then a guy named Kepler said, well, yeah, I think Copernicus is right, but moreover, if you look at the data carefully, the position of Mars, week after week after week, Mars cannot be explained, Johannes Kepler said, it cannot be explained by Mars going in a circular motion, a perfect circle around the sun. Instead, Mars's orbit must have some elongation, and Kepler tried a lot of mathematical formulas, and the one that turned out to work was the one that you learned in 10th grade. It turns out the planets actually orbit the sun not in circles, but in a shape called an ellipse. All planets orbit the sun in a shape that is elongated, mathematically called an ellipse. You may remember this from 9th or 10th grade when you learned about it. The planets go fast near the sun, and then they go, so I'll go the other way. They go fast near the sun, and then slow, and then fast near the sun, and then slow, like this. All of the planets do this, as do the asteroids, as do the comets. Even the dust particles in our solar system orbit the sun, not in circular motion, but elliptical motion. Yeah?
Why is it that the speed keeps?
The question is, why does the speed of the planet go faster there and then slowly there, and then faster there and then slowly there? I'll give you a quick answer. We're going to come back to this in a week, but it has to do with something called angular momentum, that the planet and everything in the universe conserves angular momentum, and when it's close, it speeds up. When it's far, it slows down so that the angular momentum stays the same. We'll talk more about it a little bit later. Now, let me just show you one last slide about eccentricities and the orbits that are ellipses. How does it work? Well, here is, I don't know if you can see it. There actually is an ellipse there. Can you see that? Barely. I can't. And let's try to play this thing. I don't know if I can do it. I can change the eccentricity of this ellipse. Here's an ellipse, there's the planet. Here's how the planet moves. Meow, meow, meow. Planets don't actually make that sound. In space, there's no sound, especially the way I do it. But planets do move in ellipses, and let me change the eccentricity of the ellipse. There's a more eccentric ellipse, in which case the planet goes like this. Like that. And here's an ellipse that's less eccentric. Less, oh, I better make the ellipse smaller. There we go. And finally, an eccentricity of 0 is a circle. So circular motion is a special case of an ellipse, or in other words, the circle is a special case of an ellipse. You probably learned that back in 9th or 10th grade, back when you were smart. But actual planets move in elliptical motion, and we're going to talk more about Kepler's discovery of elliptical motion, because there are 2 other discoveries Kepler made. You'll read about them in chapter 3, and we'll talk about it next time.